Well, good morning to you. At least that's when I'm recording this, and it's a very good morning. Hope you're having one as well, even if you're watching this in the afternoon or any other time. We are going to analyze projectile motion, now launched from the ground at an angle and hitting the ground again a little later. We're going to solve for the height, the time of flight, the range, and the final velocity. So we have this projectile. Here's various positions. Up, down. And it goes up and down. And so we are going to consider an initial velocity of 20 meters per second. There it is. That's V0. That's the size. And we're going to launch it at 50 degrees. Okay, so we have a Vx0 and we have a Vy0. Initial conditions, which are really quite important. And remembering that we can analyze these independent of each other. The x and the y, that is, very helpful. As we put the vector components at these various positions I show, I'm going to start with x and recognize that velocity in the x stays constant because there's no acceleration. So it's the same at every single point here. So you can add that in. So Vx0 is Vx. At any point along here, Vy is equal to Vy0 minus Gt. This is the best formula to understand what's happening to y. It starts at initial, and it's reduced by Gt as we're going up. So as we progress along here, we see that Vy is getting smaller and smaller. And up at the top, of course, there is no Vy. So V is equal to only at this point Vx. All the motion is in horizontal motion. So I'm going to draw the red vector, the final velocity vector, horizontal at that point, and notice it's the same size as these other Vx's. So now we have Vy on the way down. We'll put those in as well. There they are. And what you might notice right away is that we have symmetry on these Vy's. Okay, so if we split it down the middle, the magnitude here is the magnitude here on the vertical part. And now I'm also drawing in the additional velocity vectors that consist of the x and y components. So let's go ahead and put them in. Here they are. And finally, V final at some final angle. And as already mentioned, note the symmetry that exists in this parabola. You could split it down the center, and there is symmetry. So that's going to help us in our understanding of what's going on here. So let's now resolve V0 into components, which we show at the beginning here. And let's quantify it. So here's V0 at an angle theta. We have Vx, and we have Vy0, where Vy0 is V0 sine of theta. And if you're confused on that, take the sine of theta here. It's opposite. Oh, that's Vy0. If we add the vector on here, it's Vy0 divided by V0, the hypotenuse, and that lets you solve for Vy0 as V0 sine of theta. So that's 20 sine of 50, or 15 meters per second. Now Vx, not changing, is V0 cosine of theta, which is 20 cosine of 50, or 13 meters per second. Now we have those. Why do we want those? Because in analyzing all the rest of the vertical quantities here, for instance, the max height, we're going to be using only the vertical motion. The speed itself, the 20, does not enter in. It's 15 vertical, 13 horizontal, separate from each other. I'm going to use this equation, as you call equation 6, to find the maximum height. The height here, or the delta y, will be the maximum height right here if you solve that equation where Vy is equal to 0. In other words, when this is 0, that's the solution where it comes to rest in the vertical direction, and so that's at the maximum height. So that will give us the right answer. And h is equal to Vy0 squared over 2g. Plug in the numbers, and out pops the correct height, 11 meters. And now let's continue on to figure out the other quantities we want. So our next task is to find the flight time. And I'm going to use equation 5 for that. Notice it's only vertical quantities in here. There's no x. You got to separate x and y. So we use the form of equation 5 for vertical projectile motion. So the nice thing about this problem is that it starts and ends on the ground, which we'll call 0. So we'll make those two 0, and that'll simplify this a lot. A t goes away, and we have time up and down equals 2vy0 over g, which evaluates to 3 seconds. So the flight time is 3 seconds. That was pretty easy. Notice that this equation is a very robust equation for solving for time in projectile motion problems. The range, very simple. X direction along the ground, it's its speed times time, should say velocity, in this case Vx, times the time during which the projectile is in the air, which is the up-down time. That's the time it's traveling horizontally. So that's V0 cosine of theta, which we already solved for, but there it is explicitly again. 13 times 3, that's the time, 39 meters. Okay, our last thing is going to just be to find the final velocity. I want to make note and emphasize here, in a problem like this, do not assume that the final velocity is just the vertical speed, because that's only a small fraction of the total answer. We want the magnitude and direction of the motion, the vector velocity at the end. So here we go. We have Vx and we have Vy. Now Vy is Vy0 minus gt. So that's 15. So what it started out with, minus 10 times 3. So the vertical motion is becoming more negative by 10 meters per second every second, the acceleration. And there's 3 seconds. That gives us minus 15 meters per second. All right, what are we going to do with this? We're going to find the magnitude now, or the speed of the projectile. Squares of the sum of the squares gives us 20 meters per second. And the tangent of the angle equals opposite over adjacent. So the angle is the inverse tangent of, now the opposite is negative 15, adjacent is 13, giving us minus 50 degrees. Okay, so we have all our information. Let's just take a look at what this looks like. We have Vx and Vy at that point, and the result of those is vector V, size, direction. Well, you might notice, again, the symmetry. Compared to the initial velocity, the final velocity has the same magnitude, the same speed as it was going before, 20 meters per second. But don't say opposite direction and just leave it at that. Because if this is the final direction, the opposite direction would be this way, and that's not the launching direction. Or we launched it this way. Okay, the opposite direction of that would be this way, down and to the left here. And that's not the direction it's going. But if you think about it, it's sort of mirrored across the x-axis. So I'm going to say the opposite angle with respect to the positive x direction. Basically mirrored across the x. And that is the answer to the final velocity. Don't be lazy and only solve for part of that. Do the whole entire thing. And that will conclude this particular version of projectile motion. And next time, we will get the more general projectile motion situation where we start or end at a different height than we started. Okay, see you then.